when you have a pressure difference in a fluid, it causes a net force that does work on the fluid. And by looking at that work done as the fluid moves, we can show that this is true. Bam! It's a bunch of variables. All right, this is Bernoulli's equation. Thank Daniel Bernoulli for this. There were a bunch of Bernoullis, Swiss mathematicians, scientists, etc. Back in the 1700s, he figured this stuff out. And this tells you that if we consider some point in our flow, we have some pressure, some average linear speed of flow, and some height of our flow. This says that the pressure plus 1/2 rho v1 squared plus rho g y1, all based on that position, are equal to that same stuff at a different point in that same flow. I know it looks kind of complicated, but if you think about this as an expression of conservation of energy, it's a little bit more tractable. We have pressure, which is what's causing stuff to move. And then you have a kinetic term here that looks like 1/2 mv squared. Now these are not energies because the units are different, right? But 1/2 rho, where rho is density, which is mass over volume. So it's kind of a mass term, right? It's an inertial term, times velocity squared. So that's our kinetic term. And then we have rho g y that gives us a gravitational term. And that makes it easier for me to remember it and be able to work with it without getting too intimidated. When applying this, we can simplify it as needed depending on what thing we're looking at. For example, this is Bernoulli's equation with the full thing. Bernoulli's principle is a simplification of this that says at constant height, the pressure drops as the speed increases in a moving fluid. Here's an example with an airspeed manometer. If you've ever seen on a plane, a little tube sticking out thing, you can measure your airspeed using this device. It's a manometer, as we saw before, that you have a height difference here, and that height difference is proportional to the speed of flow. You measure the height difference and figure out the flow from that. But how does it work? It works according to Bernoulli's principle, where you have some dead zone in the front here where your velocity of flow is 0. And then you have flow of the air over the opening here that creates a lower pressure zone there because you have higher velocity that causes lower pressure. The tube facing the oncoming thing doesn't have that same thing. So you have a higher pressure here, lower pressure here. The higher pressure pushes down, lower pressure goes up there. In writing this, you can see that with that dead zone, V1 goes to 0. And now you have that pressure difference based on the speed of flow. And you can get the height being proportional to that difference. So your velocity is proportional to the square root of twice the height over the density of that fluid in there. Or actually, this is not the density of the fluid in there. This is the density of the air flowing by outside. You can be a little bit more precise with considering this if you'd like, by trying to figure out, okay, how does that exactly relate to the density of the liquid and the density of the air? Because how much is the liquid going to be pushed up based on the pressure difference and whatever. So feel free to do that if you'd like. But that's the basics of applying Bernoulli's equation to an airspeed manometer measurement.